Hi everyone, welcome back to Feedit Technologies. In today's video, I'm going to show you how to use rate-dependent data for your stress strain. So we are going to simulate axial impact crushing on a cylindrical tube. The difference is that in the previous video, we only use one stress strain data, while here we are going to input stress strain data for various strain rates. That will make your simulation more accurate. It can capture the viscoplastic behavior. So if you want to know how to deal with it, stay tuned. Okay, so this is the data that we need. That is the true stress with respect to the effective plastic strain for various strain rates. So we need to input this data, the whole data, to be able to capture or to describe the viscoplastic behavior of the sheet metals or DDQ steel in this case. So here the data point, as you see in my previous video, we used 4 data points at the plastic strain 0, 0 0.05, 0 0.2, 0 0.4. So basically it's here, it's here, it's here, and it's here. If you want, you can have like more data points to make accurate simulation, more accurate simulation. This is just for example, so I will just use data points. So in the previous simulation, in the previous videos, the last two videos that use axisymmetric and shell elements, we use data at zero point 0.1. Okay, we use data, we take this data and then we input into Abaqus. Now we want to use all the data, all the viscoplastic data, data of stress strain curve for various strain rates. So I get this data. So basically I check it manually by using this line. So this guy is 150. So 150. And then I move here, this data, it's around 230. If you want, you can use digitizer, data digitizer, like Grab It. So there's a software called Grab It, maybe, but it uses MATLAB. This is Grab It, so you can check it. Grab It, basically, you just upload the data and then you can click the data points that you want to get the coordinates. So you can get automatically the coordinate of this, and so on. Okay. So this is the data we have. So let's go into Abaqus. So this is the previous model. So if you don't know how to create this model, I will not explain from the beginning again, because I will just show you the part where you change the material properties and then we will rerun it again. So if you don't know how to do it, check out my previous video on axisymmetric modeling of axial cylindrical tube under axial impact. Okay, in this case, I will just go to the properties. So this is the axisymmetric part. So you can use it, you can use this rate dependent behavior in any kind of materials, in any kind of geometry. It can be shell, it can be axisymmetric elements, it can be solid elements. So in Abaqus, they support that, thankfully, to Abaqus. They can do it for all kind of elements. So here we click edit, density, elastic. We will not change anything. So the only thing that you need to do is use strain rate dependent data. So you click here, and then there is a one column called rate. So this is strain rate. The unit is in milliseconds. Okay. So let me tell you now. So the unit is in per second. So for example, this 100 mean 100 per second. 100 per seconds. So what is the meaning of 100 per second? It's a strain rate. So it's basically delta strain divided by delta time. So this delta time, the unit is no unit, while this one has in second or millisecond. Okay. So in our case, in our simulation, we use millisecond. So you need to make sure that here our unit is 100 per second, not 100 per millisecond. So This is what I mean. If you want to put data at 0.001 per second from your experiments, the value that you need to put in Abaqus is 0.001 10 to the power of 3, 10 to the power 3 second, right? No, milliseconds. Or it should be 0.00001 once, okay, per millisecond, or 10 minus 6 per millisecond. So this is the correct unit if you want to input the strain rate. So instead of putting 0.001, you need to put 0.000001 with 50 behind the comma. Okay. Okay. So here, let's make it 0.0001. Or instead of doing that, you can also type like this. This is also good. 1e minus 6. Okay. 1e minus 6. Okay. And then if you want to put data for another strain rate, I'm so tired to type everything. Let's just copy. Oh, this one is this data, guys. Where is it here? Let's copy, paste. Oh, I cannot paste. I need to type. Oh no. 150 to 30. Let's type 150 to 30. Sorry, guys. 325. 325 and 375. Okay, this is for the lowest strain rate. And then for the strain rate above it, the strain rate is 0.1. So it should be 1e minus 4, 1e minus 4, 1e minus 4, 1e minus 4. Okay, so the plastic strain, because as you see here, we always take the data from the same plastic strain: 0, 0.5, 0.2, and 0.4. If you have complete data, you can use the complete data. Okay, and just to clarify, for each strain rate, you don't need to use data for the same plastic strain. Okay, so it is possible that in this case you use, for example, 0.01 and 0.3. It's okay. It doesn't have to be at the same plastic strain for each strain rate. Okay, but in our case, I'm using the same one, but it is not necessary. 0.4, and then we need to I'm too lazy to do this. Let's take Excel, maybe in Excel. Yeah, in Excel. In Excel, you can copy paste. Yeah, nice. So it goes from 200 till 500. 200. Okay, nice. And then it's the same thing. Yeah, it's quicker, right? So now let's make it bigger so you can copy paste, 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 paste. See, it's good, right? And then strain rate, you need to 0.1. 10, 10, 10. Oh, you multiply by 10. 1e minus 3, 1e minus 3, 1e minus 3, e minus 3, 1e minus 2, 1e minus 2, 1e minus 2, 1e minus 2, 0.1, 0.1, 0.1, 0.1. That's it. So 0.1 here, it doesn't mean 0.1 per second. It's a 100 per second, right? Because the unit was different. Here, we're using not per second, but per millisecond, okay? And then you click OK. So that's it. If you want to use temperature dependent data, you can also do the same thing, but we will not discuss here. We are going to focus only on the strain rate dependent data, okay? Because this is the impact case, and hopefully, and one thing, let me clarify. I think when you put this number, this should be like in ascending order. The lowest, higher, and lowest, higher, higher, higher. You cannot put like 1e minus 5 here, 1e minus 3, 1e minus 2, and then 1e minus 4. You cannot do it. You need to have it like in a good order, okay? They will give you error if you don't do it. And then let's run it. I think that's the only thing you need to change. So it's a very simple process actually. Instead of using putting data point like that, oh, there is error. The static yield stress must be defined first. Okay. So you need to define a static yield stress, and this is a bit strange. Oh, not strange. I mean, I'm sorry, I'm using the wrong word. Uh, so you need to define a static yield stress. So what happened actually is that Abaqus will interpolate data from this data point to another data point for different strain rates. So when doing that, Abaqus need to have data at a static strain rate. Usually, when you're simulating, for example, metal, they consider 10 to the minus 3 or 10 to the minus 4 per second as a static data. That's what they usually consider. So this one, you can put 0, I think. Instead of putting the real strain rate, you can put 0. That should be okay, because as the strain rate goes lower, actually the effect of the strain rate becomes like not significant enough. So changing this from 0.001 to 0, it will not change a lot, because for example, if I do another test here, maybe my curve will not be here. I mean, my sorry, you understand what I mean? My curve will not be like this. Maybe my curve will be like almost, how you call it, superimposed to the 0.001. So the rate sensitivity becomes lower, or becomes more insignificant as you go to the lower strain rates. That's why people limit at 0.001 or 0.0001 per second in their testing experiment, because you can do very low strain rate like 10 to the minus 7 per second, but your tensile testing is going to take like forever, like 1 month. You don't want to do that, right? And then you click OK, click job. So yeah, so the only difference from what we do right now, by putting all the data instead of using any specific model like Johnson-Cook model, Cooper-Simon model, is that in terms of industrial practice, it's easier, because you don't need to do, you remove one step calling fitting parameters, right? You don't fit anything, right? So you just put the data. So it is simple, right? But the limitation of doing this is basically when your elements experience strain rate higher than the data that you supply. For example, in this case, our maximum strain rate is 100 per second. Imagine that in one of element that you have in your model, the strain rate reach like 1,000 per second. Abaqus will only use the 100 per second data. They will not extrapolate it, and even if they extrapolate it, you need to tell them how they extrapolate it. But in Abaqus, they don't do it. Okay, they don't extrapolate it. They just use the highest data that you supply, the highest trade rate that you supply. But when you're using the model, your model has a certain formula, like maybe exponential, logarithmic. So when you are out of, I mean, you don't supply anything, you just supply parameters. So regardless of the, I mean, even if the strain rate goes like 10 million strain rate per second, right? I mean, your finite element simulation can always get the stress data at that strain rate, even if it's like too high. Yeah. So that's the benefit of using a considered model that has the specific formula like Johnson Cook or Cowper-Simons instead of supplying data directly like this. It's running right now. Okay. So there is no problem regarding the rate dependency. And then we are going to compare the stress strain curve from this kind of simulations and from the previous simulation that we used before. So let's open the previous, it's in FIDIT 10, I think, in the previous simulation. Let's open the ODB, right? I think this is the ODB. And then there's a 0, right? Create ODB. Let's process the data so we can compare quickly. And then we want to compare the reaction force unique nodal, reaction force RF2, and then the node set. It's set 1, I think. We can highlight. Oh yeah, it's if you see in the previous video, I cannot highlight this. Sometimes it just don't show up like this. This one is good, and then we save it. Okay, and then you can, yeah, see, this is the data from the whole nodes. Now we need to sum it. We go operate on XY data, continue, and then we need to sum double bracket, and right in this middle you click here, you click here, you add to expression, you save. Okay, and this is this first summation, the force versus time, the one that we want to get. This is strain time versus force without strain rate. Okay, without rate dependency. And you can see here we plot, this is the reaction force. Let's copy here. Okay, this is without strain rate dependent data, and then we are going to compare with the one with rate dependent data. Hopefully we can see some effect, because as you see, I think in my previous video about these axial crushing videos, I showed you that locally the strain rate is somewhere between 10 to 100 per second, while the data that I supply is 0.1 per second, so it's really low. So the data that we are running right now, if the simulation works fine, it should give you higher force, because now your material becomes hardened. Okay, it takes a long time. So with the power of editing, here is the new result. Okay, so now it's finished. Click dismiss. But before that, to avoid confusion later, let's close this ODB from the previous file. File, close ODB. Yeah, so this is FIDIT 10. This is the old file. Click close. And then you go back again to the job. Then click result. Now this is FIDIT 11, the one that we are doing right now. Okay, as you can see here, it is way much stiffer. It is more difficult to bend, right? Only 2 fold. If I'm not mistaken, in the previous video we have 3 folds, right? Okay, now let's calculate Let's calculate the, how you call it, the reaction force. Will ODB output reaction force, and make sure you delete the previously get data. Yeah, just remove this and also this, so they are clean, empty. And then in terms of node set, this node set first one, okay, then you click save, click okay, go here. Now you have the full data, and then you sum all of them. Continue. You type sum, or if you want, you can click this here. Summation. This one. And then you click the first one, go down, press shift and click and add the expression. You save as, click OK. So this is the second data that we have. Click here, go drag below, click here, press shift and control C, and you go here, paste time force, you paste this one, delete the O, so it's width strength rate. You go here, you click here, you press shift, you pitch down, you press control and pitch down, and then insert this, yeah, you see, and then you control X, you click here, and then you control V. As you can see here, when you input strain rate dependent data, your peak force can go up to 140. I don't know how, what is this? It's Newton, I think, kilonewton. So previously was 80, now it's 140, and it's higher, right? So if you take the average, the mean crushing force, MCF, so the force that is required to crush your structure, if you take the average, if you take the mean value, or what we call mean crushing force, they are usually higher as you use strain rate dependent data, and more that is actually more accurate, instead of using stress strain rate data from one strain rate. You understand what I mean? Like in my previous video, I only took one curve I put for that strain rate, but in reality I will never know what is the strain rate in these elements, right? Because as you can see here, the plastic strain, if you go here, this is the plastic strain. The plastic strain is different everywhere. So of course, the plastic strain rate also different. So we cannot just supply one data from one strain rate, because it is not necessarily that this element experience those strain rate that we give. So we need to give like several curves. So what we just did today, we give several data for various strain rates. So Abaqus will interpolate data between them, right? So I think it's enough for today. I hope it's useful for you. It's giving you more experience on how to deal with rate dependent data. In the next videos, maybe I will put more videos related to using specific model like a Copper Simons or Johnson Cook model. So I will try to show you how to do it. And goodbye.